So, hi everyone. So I'm Jean Nippert. I'm PhD student for the STELLA experiment at IPHC in Strasbourg, and I will present you the 12 carbon fusion reaction at deep sub-barrier energies with the STELLA experiment. So, to start, I will present the astrophysical interest of the carbon-12 plus carbon-12 fusion reaction and present a bit the reaction itself. Then I will talk a bit about the resonances and Hindrance. I will then explain a bit the STELLA experiment, describe it, and then talk about the specificities of the analysis and some results. So at start, the Big Bang leaves us a universe full of hydrogen and a bit of helium. Those light elements are evolving in stars through fusion. So first, the hydrogen become helium, and the helium become carbon-12 through the 3-alpha reaction. So if you look at this graph showing the abundances with respect to the mass number for the chemical elements in the solar system, you can see that you have hydrogen and helium, then a gap, and then the carbon. And the carbon is basically the bottleneck to the creation of all the heavier elements, as you can see on this chart of nuclei. So, what is really important in astrophysics will be the carbon burning. And the carbon burning, basically, in stars, it mainly occurs through the carbon-12 plus carbon-12 fusion reaction. And this gives you the magnesium-24. And if you, for example, if you look at this energy diagram, you do carbon-12 plus carbon-12, and you will populate the magnesium in approximately around this red point. It's in a high excited state, so it will release the energy with evaporating a proton or an alpha, creating respectively the sodium-23 and the neon-20. And those two nucleus can also be in an excited state and emit a gamma for the disexcitation to go to the ground state. For the sodium-23, for example, it's the first excited state is 440, and for the neon-20, it's 1634 keV. So in stars, those reactions will occur at temperature around the billion Kelvin. For the minimal mass for the stars to start the carbon burning, it's a bit discussed. If you look at this graphic showing the minimum mass to start the carbon burning function of the metallicity, you have two principal information. First is that it depends on the metallicity. And the second is the most important one, is you have two types of model that describe the fusion reactions in this plot. And what we see is that there is a lot of difference for the minimal mass function of those models. So this means that it's really important to measure the most precisely possible this reaction to better understand the astrophysical implication, and that's why it's really interesting. So in stars, the energy of the particles is thermal energy, and so it will follow a Maxwell-Boltzmann distribution. If you take, for example, 1.5 billion Kelvin, it gives you a peak of the Maxwell-Boltzmann around 130 keV, and this is really low energy and really challenging for nuclear experiments. If you compare it, for example, to the carbon-12 plus carbon-12 Coulomb barrier, that is 6.6 MeV, you see that the reaction will have to go through quantum tunneling, and that leads directly to very low cross-section. What we try to measure is a cross-section around the picobarn level, down to the picobarn level, and this is really, really challenging. If you look, for example, at this scheme that shows the Maxwell-Boltzmann distribution in blue and the probability of tunneling through the Coulomb barrier in red, you can take those two curves and do the convolutions, and it gives you the green curves. And the green curve is basically the Gamow peak that gives you the energy window in which most of the reactions will occur in stars. We have very low cross section because of the quantum tuning, and this is the first challenge we will have to measure this reaction for the astrophysical interest. Now let's take a look at the cross section. So here you have the cross section function of the energy a little bit below the Coulomb barrier, with cross sections that are still quite easy to measure. And what we see directly is that you have a lot of resonances in it, and some of those resonances can be associated at molecular states in the magnesium-24. But what exactly are molecular states? So Ikeda had the idea that at some inside the nucleus, you can have configuration of lighter nucleus, and for example, in the magnesium-24, you can have a neon-20 plus alpha, carbon-12 plus carbon-12, or other more complex configuration if you go up in energy. And we had some evidence of it experimentally, but in the theoretical part, it was quite hard to explain. And Ebro and collaborator did explain it doing a microscopic calculation of it, and they saw, for example, in the magnesium-24, some configuration of 2 carbons or oxygen plus 2 alpha, and so on. And those molecular states are really important because they are favorable configuration that will increase. That will increase the cross section because it's favorable state. And experimentally, we can measure those states with measuring the angular distribution, and this is possible with the STELLA experiment, but I will talk about it a bit later. But now, what if there is such resonances at low energy in the astrophysical region? It can have a huge impact of our comprehension of the stellar evolution and the nucleosynthesis. So now that we are getting to the point of the astrophysical region of interest, let's talk about Hindrance a little bit. So what is Hindrance? So Jiang and collaborator in 2002, they measured fusion cross-section for nickel 58 plus nickel 58 and zirconium 90 plus zirconium 92. Here you can see the excitation function of the energy normalized by the Coulomb barrier. And what we can see in this graph is that when you go down the Coulomb barrier, you start to have some discrepancies between experimental data and the coupled channel calculations that are the dashed line. And this is very surprising because at this time, the coupled channel calculation was really, really good to describe fusion cross-section. And now it has been observed in most of the system. And so theoreticians started to explain the phenomenon to understand what's going on between this Hindrance phenomenon. And there is one particular interpretation from Cedric Simonel and collaborators that is basically including into the theory the exact polyrepulsion by antisymmetrization of the wave function. And the results are in the left. So basically, you have the potential on the top and the fusion cross-section function of the energy on the bottom. For two systems, calcium 40 plus calcium 40 and calcium 48 plus calcium 48. The frozen artery theory is the theory they used before, and the new theory with the polyrepulsion is the density constraint frozen artery in red. So basically, what you can see is that in the potential, you see that the Coulomb barrier is wider, and we say wider Coulomb barrier, say lower cross section, and in the results, it seems to work quite well for the calcium 48 plus calcium 48. Here you see that the blue curve didn't reproduce the data, while the red curve is pretty good at reproducing it. And for the calcium 40 plus calcium 40, it's still better than the frozen artery fog theory, but the density constraint frozen artery fog still miss something because you can still see a little bit of discrepancy. Now, what if we look at the carbon 12 plus carbon 12 system? So basically, you have on this plot showing the S factor function of the energy. You have the black line that is the density constraint frozen artery fog, and the red line that is the hindrance, which is a phenomenological model presented by Young and collaborator. And the density constraint frozen artery fog theory doesn't see hindrance in the carbon 12 plus carbon 12 fusion reaction. But there is still a lot of debate for this particular system. And you can see it with the amount of publication on this subject as theoretical and experimental for the last 20 years. So you see with that it's really a challenge to understand as theoretical and experimental point of view. And this is why it's so exciting to measure such a reaction. So now let's see how STELLA is built to measure such cross-section. So I recall the main challenge is that we have a very, very low cross-section to measure. And that means that the signal will be really low compared to the background. So what we need is background reductions, intense beam, and very long time measurements. We are talking about months of measurements. So I recall carbon 12 plus carbon 12 gives you sodium 23 plus proton plus gamma, or neon 20 plus alpha plus gamma. So what STELLA is using is coincidence technique. So coincidence between charged particle and gamma. The gamma will be measured by 36 scintillators that are lantern bromide from the UK collaboration FATIMA, and those have the advantages of having a good resolution and a very good detection efficiency. They also have a timing resolution lower than the nanosecond, and that is really important for the synchronization for the coincidence technique. And we will come back about a bit later about this. Just to give you a hint, this is a spectrum for one particular kinematic line that is P1 at the energy of 2.16 MeV in the center of mass system. So we are really deeply under the Coulomb barrier, and the signal is really, really, really low. And you can see two lines. You have the black line that is the proton line that we want to measure, and you have the second one, the blue one, that is carbon interacting with the deuterium of the water that contaminate the target. And at this energy, the reaction with the deuterium is really, really stronger than the signal from the proton line. And you can see on the top the the spectrum cleaned with the coincidences, and you can see that you don't see any deuterium anymore, and this is really the strength of this experiment. So now the charged particles, they are measured inside this chamber that is closed by 1.5 aluminum dome, 1.5 millimeter thick aluminum dome, and you can see on this scheme the yellow arrow that is basically the beam. It's crossing a target. It's a self-supporting thin rotating target foil that can go up to 1,000 rotations per minute, and that allows its dissipation because we need really intense beam. We have 3 DSSSD, 2 S3 and 1 S1. They have the granularity that allows angular distribution measurements. We also recently had another detector that is Pixel. I will talk about it a bit later. And we have elastic scattering monitoring to help us normalize the data and verify the target integrity. So everything is in a vacuum that is insured by a cryogenic pump, and the vacuum can go down to 10 to the minus 8 millibar. Just to add, so we need to measure the most precisely possible the cross section. So we also have a target thickness measurement station that allows us to measure target thickness. So basically, here you have the chamber on the photo. Here is the acquisition system, and inside the chamber you have an alpha source that is americium source. You have a collimator, and this is a strip-driven scan, and we measure the energy loss of the alpha in the target with a silicon detector. So recently we added some improvement with noise reductions, temperature stabilization, a pulsar method to follow the evolution of the gain, and we also alternate on and off beam spot to verify that the measure is consistent. The results are that we have less than 10% uncertainty of the thickness of the target, and we also observed sinusoidal dependency of the thickness of the target. So basically, that means that we have a linear variation of the thickness through the diameter, but this doesn't really affect our measurements because we are using those target rotating. Okay, so now let's see a bit of results. So those are angular distribution measurements. So you can see a differential cross-section function of the angle. And this is at an energy of 5.38 MeV in the center of mass system. And it's for the carbon 12 plus carbon 12 that gives you neon 20 plus alpha 0. So the ground states of neon 20. And so what we measure is basically the angular momentum of the alpha particle by fitting the data with Legendre polynomial. So on this plot, you can see in red the cross sections that are measured by the detector, and the gray points are basically just the symmetry around 90 degrees. And what we saw here is that basically the Legendre polynomials of order 8 is the one that describes the best data. But what we also see in this plot is that in the middle we have a lot of lack of data. So the angular coverage is not enough to restrict all the parameters for the Legendre polynomials. And this is this is why we added a new detector that is Pixel that will be around 90 degrees, and this is first idea of what it will get us. So this is Pixel. So here you see in this photo the BB10 version that have better granularity. So for the angular distribution, it's better. We also have SUPER-X3 model that have a better timing, so it's more for coincidence. So basically, we can have a better angular distributions, but also increase the solid angle for the lower cross section. In this spectrum, it's a simulation. So this is for carbon 12 plus carbon 12 that gives you neon 20 plus alpha for the different excitation. So what we see is that basically around 90 degrees, we will have a better angular coverage. And pixel now is around 60 to 90 degrees. So it will very nicely help us to restrict this part of the spectrum, this part of the data, and we will be able to restrict very well the Legendre polynomials. So these detectors have just been tested in a recent experiment that ended this morning, and so we will keep you posted with the results. So now let's go back to STELLA. So STELLA is basically coincidence between gamma particles and charged particles inside the chamber. And those coincidences, they have a timing gate thanks to the 2DAC of 15 nanoseconds. And this is really important. You can see already this gate on this plot. So this is the energy versus the time difference between the measure of the gamma and the charged particle. So here you can see, for example, P1 signals, and you can see that the gate of this signal is basically 15 nanoseconds. And why is it so important? Because if you look at this red curve, it's basically just a separation between the alpha signals and the proton signals, meaning that we can measure exclusive cross sections for proton and for alpha. That also means that for an alpha that have the same energy of a proton line, we can distinguish the two signals, and this is very powerful. And this spectrum is basically in coincidence with every gamma. Now we have 36 scintillators with self-activity. Self-activity means that we can calibrate our scintillators hour by hour. That means that we can do very long stable measurements. And this allows us also to very nicely select gates on the gamma energy for the 440 kV and for the 1634 kV. And if we gate on those two gamma decay, we get the spectrum on the right side. So you can see that a lot have been cleaned, and you have two boxes. The black boxes is for alpha 1, and the red boxes is for proton 1, for P1. So basically, here you can see the signals we want to measure. So we select these signals, but you also have the dash box. The dash box is here to understand the background. So we can estimate the background using this, because what we know is that when you have false coincidences, it basically happens randomly in time. So we can select in the right time the signals and select in the wrong time the background and estimate it. And so we can measure, we can compute the cross sections and have a very good precision on the error bar. So here are some results now. So you can see S factor for the alpha channel and the proton channel. So you have in gray the previous work of other experimentalists, and in red the present work of the STELLA experiment. You also have two models. It's the Fowler in blue that are usual couple channel calculation, and you have the phenomenological model that is Hindrance, designed by Jiang and collaborators. And so we can see several things. So we have three principal regions. Above 4.5 MeV, we basically validate the coincidence technique. Between 2.5 and 4.5, we basically see that the Fowler overestimates the cross section almost all the time, and above 2.5 MeV, we have sign of hindrance plus resonances at around 2.1 MeV. So I say that because we did a chi-square analysis with our results below 2.5 MeV, and it's in a better agreement with hindrance model plus resonances here that also have been claimed by STELLAJean, and then for the Fowler model or for the hindrance model alone. So those are the STELLA's results for this for this experiment. So now that we have S factor, we can see a bit of astrophysics with it. So recently we published reaction rate and the impact on stellar evolutions, and this is a little overview of what we did. So I put you back here the S factor for the proton channel. You have the Hindrance model in red, the Fowler model, so coupled channel calculation that also can be called CF88. And basically, we calculated the reaction rate for three types of models. So the CF88, that is the normalization here. So we have reaction rate normalized on the Fowler rates. And we have hindrance model and hindrance plus resonance model that are fitted with the STELLA data. And so in red here, you can see that where STELLA have measured. And it gives you a very interesting information, because here you have some arrows for 12 solar masses and 25 solar masses for two different models, hindrance and hindrance plus resonance, and this represents the Gamow window. So basically, the astrophysical interest for those masses of stars. And what we see is that we already measured in those Gamow windows. The thing we need now is better precision, but it's already a very good information. And so what we see in the reaction rate is that basically for the hindrance plus resonance model, we are very close to the Fowler rate in the region of interest for those mass of stars. But for the hindrance model, the cross section is another order of magnitude lower than the Fowler rate, and this will have a little impact that I will show you just now. So this is a collaboration with the Geneva Observatory and also the Brussels Observatory. And for the two first plots I will show you here, it's with the Geneva collaboration. And so what we see here is the temperature inside the center of the star during the carbon burning phase. And it is for the three reaction rates that I showed before. So basically what we see is that the CF88, so Fowler rates and hindrance plus resonance rates are pretty similar. The evolution of the temperature during the burning phase is pretty similar for those two models. But for the hindrance, we can see that the temperature is really higher. And this is for the two different mass of stars. And why it's like this is basically, so the star is in equilibrium between the gravitation and the pressure created by the fusion. And basically, the stars will need to have the same rates all the time. So with the hindrance, the reaction rates are lower. So basically, the star has to contract itself, and the temperature will be higher, and the density also will be higher. And in the Kippenham diagram, you can see the impact of this higher temperature and higher density. Is that basically you can see here the distance inside the star, and with respect to the year, so to the time. And what we can, the information we have with that is that the carbon burning phase is almost twice shorter than for the hindrance plus resonance. So this is the main impact for the star evolution. Now let's talk a bit about the nucleosynthesis. So for the abundances, it has been calculated with Arthur Chopin from Brussels, with the nuclear in a box with nucleosynthesis in a box. So basically, what we can see is that you have quite some difference for the hindrance plus resonance model for sodium, aluminum, and phosphor, but for the rest, the difference is quite modest. So basically, those the hindrance plus resonance doesn't affect that much the nucleosynthesis, but this there is still a lot to investigate for the nucleosynthesis, and mainly with the minimum solar masses to start the carbon burning. And I heard that a lot of astrophysicists are interested to work with those reaction rates. So let's see what they get. So just to conclude, nuclear astrophysics direct measurements in light system of astrophysical interest are really challenging, and basically with STELLA we can measure that pretty well, and mainly through background reduction. We have a possible evidence of hindrance behavior with a resonance. We will be able to measure a better angular distribution with the addition of pixels, and determine angular momentum with it. So for the astrophysical interpretation, the stellar reaction rate with the stellar reaction rate, we saw that the impact is quite modest for the stellar evolution, but there is still a lot to learn about the nucleosynthesis. So there are new results that will come in the next time. And there is a new experiment that just ended this morning, so let's keep posted. And I want to thank the STELLA collaborations and all the collaborators we are working with, and thank you for your attention.